Welcome back. In the second part of this section, we're going to talk about vertical asymptotes. So of course we know what a vertical asymptote looks like on the graph. It's a place where the function is becoming either infinitely large or infinitely small on the left side and on the right side. Maybe it's doing the same thing on both sides. Maybe it's doing different things on alternate sides. But either way, as long as the graph is doing one or the other flavor of infinity on both sides of C, then the function has a vertical asymptote at C. So we need a way to detect the existence of these vertical asymptotes, and here's a theorem that can help us out. So we've got ourselves a function that's a quotient, and the numerator is a continuous function, and so is the denominator. The denominator is some sort of continuous function. They're both continuous on this interval that contains C. The function needs to not be equal to 0. The numerator, needs to not be 0 at C, and the denominator is 0 at C. We also have here that the function is not 0 everywhere else. Otherwise, you run into problems. Like if you had the numerator was some polynomial and g of x was always equal to 0, then that would not give you vertical asymptotes. That would give you a function that's just undefined in a bunch of places. So specifically, your denominator is equal to 0 at C, but it's not equal to 0 everywhere else. It's not equal to 0 in all those other locations around C. So now this theorem promises us if that's the case, if the numerator is not 0, denominator is 0, you do have a vertical asymptote, but that's not an if and only if statement. So having a vertical asymptote doesn't mean you have to have a numerator that's not 0 and denominator that's 0. You can have something where the top and bottom are both 0 and you've got a vertical asymptote. So as an example of that, a function like y equals x over x squared. At x equals 0, the numerator is 0 and the denominator is 0, but actually you've got a vertical asymptote at 0 because this function simplifies to give you just 1 over x. So actually this function is equivalent to 1 over x. You have a vertical asymptote at 0. So this theorem can help you when it's not in the form of 0 over 0 to detect vertical asymptotes. But same thing as before, if things are 0 over 0, you're going to need to think about using limits to figure out what's going on. And that's, I guess, the moral of the story for this whole section. That's why we're talking about infinite limits, because we'll be doing all this investigation with limits. So I've got couple of functions that have some discontinuities, and of course we want to be able to figure out what is the nature of that discontinuity. So if I'm looking at this function, the 1 over x, x minus 2, for sure the discontinuity for this one is at x equals 2. So I know that this one is discontinuous at x equals 2, and that's the only place where we have a discontinuity. For rational functions, it's just where the denominator is 0 that you have to worry about. So that's our discontinuity. The question is, what kind of discontinuity is it? Do we have a hole? Do we have a vertical asymptote? If it's a vertical asymptote, what is the graph doing on either side? So that's why here I'm looking at both the left side and the right side separately. So I'm going to look at the numerator first at this one, and I'll say for the limit x goes to 2 from the left of 1 minus x, and then I'll do the same thing for the denominator. So the limit for the numerator as x goes to 2 from the left would be just 1 minus 2, which is negative 1. So our numerator is negative. And the other thing that we can say is for the denominator is that as x is going to 2 from the left, x minus 2 itself is going to be some number smaller than 2 minus 2. We're going to wind up with something that's negative. So our numerator is negative. Our denominator is negative and is approaching 0. And our numerator is negative. So as x approaches 2 from the left, we're going to wind up with something that is negative over something that is negative, which is going to give us something positive. We're going to wind up that this is diverging to positive infinity. So again, the reason we're going to have some sort of vertical asymptote is because the top is going to not zero and the bottom is going to zero. And now what kind of asymptote? Is it because the function's approaching infinity or approaching negative infinity? Well, that's where I need to start thinking about the signs of things and how does that affect stuff, positives and negatives. Similarly, if I look at the denominator, sorry, if I look at the bottom, whether I'm looking at x going from 2 to the left or looking at x approaching 2 from the right, it's really the same for the numerator. It's going to be approaching -1. So that's true for the both parts of this problem. And if I'm looking at what happens as x approaches 2 from the right, x minus 2 is going to be something bigger than 2 minus something that's exactly 2. You'll wind up with bigger minus smaller. You wind up with something that's positive. So we've got something negative divided by something positive. So in other words, we're talking about negative values. The numerator goes to 1. The denominator goes to 0. I can say that this will diverge to negative infinity, because I'll have numerator numerator going to -1 and denominator going to 0, and that denominator is going to 0 through positive values. So it's always negative divided by positive, which gives us something negative. That's why it's negative infinity. So that's how I know, for example, for this graph, if I felt like graphing it, at x equals 2, there would be a vertical asymptote, and I know on the left side the graph would be approaching positive infinity, and I know on the right side of 2, the graph would be approaching negative infinity. Okay, last little one to do here. This function, again, another rational function, and we can already see at the very top, these are going to have two places where we have discontinuities. We're discontinuous at x equals 1 and also at x equals -1. And I know that because if I were to look at my function, this x squared minus 3x plus 2, I could see that actually the denominator factors as x minus 1, x plus 1. And actually, if I wanted to, and I think this is a good idea to do so, to simplify things already at the outset, and note that my function can simplify to be the same thing as x minus 2 over x plus 1. So now when I'm looking at my limits, really I can look at the limit of this function, but we'll get to that for each of these examples. I'm looking at in two places as x goes to -1, what's going to happen as we approach it from the left and from the right. And here I'm asking us just to look at the limit as x goes to +1, period. In other words, approaching 1 from both sides. So I guess I'm confident that this is going to be some sort of number then. So let's start off with the first one. We want to know what's happening as x goes to -1 from the left. Okay, so if we were starting with this one and we wanted to know what happens as x goes to -1 from the left, on the bottom, as x goes to -1, from both directions, it's going to 0. You're going to wind up with 0 in the denominator. And then the question is, well, what happens as x goes to -1 for the numerator? And for the numerator, as x goes to -1, whether it's from the left or from the right, x squared minus 3x plus 2 will go to -1 squared minus 3 times -1 plus 2, which is +6. So I also know, as I said before, that the denominator is going to be 0. And I also can talk about whether the denominator is getting to 0 through positive values or negative values. So as x is going to 1 from the left, from smaller values, slightly smaller values of x, so like 0.99 or 0.97, things like that, what happens to our denominator? What happens to x squared minus 1? So if we had a number slightly less than 1, and we square it, slightly less than 1 and squared it minus 1 would be smaller minus larger would be something negative. So as x goes to 1 from the left, x squared minus 1 is negative. So top is a not zero number, bottom is 0. That's telling us we have a vertical asymptote. The top is positive, the bottom is going to 0 through negative values. Positive divided by negative is a negative, so that means we must be approaching negative infinity. Same sort of reasoning I'm going to say for here. So similarly, the x going to negative 1 from the right, the numerator is going to go to 6 in that direction as well. And for the denominator, that's also going to go to 0. And so now the question is, what happens as x goes to 1 from the right? What happens to the denominator? Is the denominator always going through positive values, or is it going through negative values? So as x is bigger than 1 a little bit, so for numbers slightly bigger than 1, squaring them and then minusing 1, you'd have slightly larger number minus slightly smaller number. That would be something positive. So if x were a little bit bigger than 1, then x squared minus 1 would be positive. So top going to 6, bottom going to 0 tells us we have a vertical asymptote. The top is positive, the bottom is always positive, so positive divided by positive is positive. Our limit must be positive infinity then. So on the left side of negative 1, we're going to negative infinity. On the right side of positive 1, we're going to positive infinity. Okay, so last one that I want to do, and that is the limit as x goes to positive 1, and this is approaching positive 1 from both sides. So if I were to put in positive 1 right now and evaluate the numerator and the denominator, the limit for the top as x goes to 1 would go to 0. The limit for the bottom as x goes to 1 would go to 0. We'd have 0 divided by 0, and we know that's an indeterminate form, so that's a sign that you need to do some sort of algebra. And I did the algebra actually already on the side here. I know that if I were to simplify my function, it simplifies to give me x minus 2 over x plus 1. And now I can evaluate this limit because as x goes to 1, the top is going to just a nice number. That's going to negative 1. And the bottom is also going to a nice number. It's going to 2. So our limit actually is a half. So what does that mean for us? Well, our graph is approaching negative a half on the left side and the right side of 1. So at 1, nothing's happening. But at 1, the y values are getting close to 1/2. In other words, we have a hole in the graph at 1/1/2, as opposed to at negative 1, where on the right side we're going to positive infinity, and on the left side we're going to negative infinity. So we have a vertical asymptote at negative 1, and we've got a hole at x is equal to 1. Okay, a couple little notes in this theorem that are really good to know that will help us evaluate some infinite limits. So we've got one function who's having an infinite limit and another one whose limit does exist. So g is the function whose limit exists. It's some real number L, and f is a function whose limit is positive infinity. And these are as x is approaching some number c. So the first thing that we have is if f is becoming infinitely large plus a finite number is infinitely large. And same thing with infinitely large minus a finite number is infinitely large. So if one of our terms is going to positive infinity and the other term is going to some finite number, then I could just say the limit for that whole thing is going to infinity. And you could say a similar sort of thing about what if the function was going to negative infinity. So if f was going to negative infinity plus a constant would be negative infinity. So same sort of idea. We have another one here about products. So if we're looking at f times g, if again f is going to infinity and g is going to some finite number, two options. One is if the number is positive, then a positive number times positive infinity would give you infinity, and a negative number times infinity would give you negative infinity. You'll notice that there's no mention here about L being equal to 0. So like what happens if G's limit was 0? That is not covered by this theorem. This theorem will tell us what to do if you're looking at F times G and G's limit is positive or G's limit is negative. But if G is 0, sorry, this theorem does not help you. If we have a fraction, so if we have a quotient and g is on top and its limit is a positive or negative real number or 0, doesn't really matter for 3, and f is going to positive infinity, then the whole thing is going to 0. And that one is also the same that you'd make if f was going to negative infinity. If f was going to negative infinity, then g divided by f would also be going to 0. So the big caution that I mentioned there with the second part of that theorem was about what if that limit that was a finite real number, what if it was 0? And that's a problem because we know from before infinity times 0 is indeterminate. So that's the reason why our theorem doesn't cover that form. If you did have something that was infinity times 0, then that's not something where we can just evaluate and say, oh, that will be 0 or that will be infinite. We'll have to do something with it. I mean, a good example of that, of 0 times infinity being indeterminate, is that sine of x goes to 0 as x goes to 0. 1 over x, as x goes to 0 from the right, it goes to infinity. So sine of x times 1 over x, that's a 0 times infinity, and some people might say that's infinity, some people might say that's 0, but both people would be wrong because sine times 1 over x is the same thing as sine x over x, and we know from 1.3 that that has a limit, and the limit is 1. So if we have something where it's 0 times infinity, we'll have to keep in mind that's indeterminate. That means do something to it to figure things out. Unfortunately, you can't just make a conclusion on something that's indeterminate. So let's use our theorem to help us out with these little 3 examples. So for the first part, I know that the limit as x goes to 1 from the right of x plus 2 is just going to be a nice little finite number. That's going to be 3. And if I'm looking at the limit as x goes to 1 from the right of 1 over x minus 1, so if I'm looking at numbers a little bit bigger than 1 minus 1, so bigger minus smaller, that would be something positive. I'd have something going to 0, but through positive values, that would be 1 over positive, getting close to 0 is positive infinity. So now I can say, well, for this, we're looking at the limit of constant plus infinity, which is infinity. That was our very first one of those 3 theorems that we had. The first said that if you had one function was infinite for its limit and the other one was a real number, then the limit of function, 2 functions added together would be infinite. Okay, let's do the next one. So I'm looking at the limit as x goes to 0 from the left. So x minus 5, for sure, that one's just going to be a constant. X goes to 0 from the left of x minus 5, that is just negative 5. And if we're looking at the limit as x goes to 0 from the left of cosecant, if you're having trouble with that, you can think about it as the limit as x goes to 0 from the left of 1 over sine, because of course cosecant is the reciprocal of sine. And then you can ask yourself, okay, if I'm thinking about my graph of sine, I know as x is less than 0, is a little bit less than 0 value, sine is negative on the graph there. So I'd have 1 divided by negative numbers, getting closer and closer to 0. That would be going to negative infinity. So it looks like what we're going to have now here for this limit would be a negative real number times negative infinity. We'd have a negative times a negative. That would give us a positive. We would have something that is positive infinite. Okay, last one at the bottom. So the numerator looks like it's going to be something finite because as x is going to pi over 2, sine goes to 1, so 2 plus sine goes to 3. And I know for the denominator, we're going to pi over 2 from the left. And for the denominator, as x goes to pi over 2 from the left for tangent, I know for the tangent function that it has a vertical asymptote at pi over 2. And on the left side of pi over 2, we are zooming off to positive infinity. So it looks like we've got a finite number divided by infinity. Our limit theorem from previous page told us that that limit would then be 0.